All right, folks, we're now ready to jump to the next section of the next section of alternating current, which is transformer. Too excited to move forward. Okay, so now transformer is something that actually has been taught in secondary school, right? So what's different now? It's Cambridge expects us to apply the rules of EMI, right, into understanding the transformer. So the first thing that you should know, right, is that when you have an ideal transformer, okay, the magnetic flux is actually the same on the primary coil as well as on the secondary coil. Right? So what this will also means is that the rate of change of flux is going to be the same. Okay, just a recap. Magnetic flux is you can visualize it as the number of field lines. So there'll be equal number of field lines on the primary coil as there are on the secondary coil. Okay. Now, because in the EMI, we have learned Faraday's law, right? So what Faraday's law tells us is that the voltage is actually directly proportional to the rate of change of flux linkage. So since the rate of flux change, right, this one is actually the same on both coils, then I can express the primary coils by Faraday's law, right? Okay, the voltage over here is going to be negative Np, number of turns of the primary coil, d phi dt. And then for the secondary coil, similarly, it is negative Ns d phi dt. D phi dt is the same, right? So I don't have to separately write, a subscript for each of these flux. Okay. If you were to take equation 1, divide by equation 2, right? So then what you will find is that Vp over Vs, it's going to be Np over Ns. Okay, and so it's simply just memorize or remember this one, right? It's simply telling us that the induced voltage is proportional to the number of turns of the coil. So in this, let's say I turn this into a numerical example, right? So suppose you were to count on the primary coil side. I think there are about 16. If I can count, I think it's 16. Okay, so let's say there are 16 turns on the primary coil side, and then on the secondary coil there are 7. Okay, so suppose I tell you that the primary voltage, let's say the RMS voltage, is 32 volts. See, so what this will then mean is that by proportion, then the secondary voltage, right, should be 7 over 16 times 32, right, giving us 14 volts. Okay, now that's the first rule, right, that you need to recall. All right, now see, at first glance, right, you think that the conservation of energy is violated because then you can kind of like happily raise voltage, decrease voltage as you like. If I want to, I can make this 16 turns and then this one like 16 million turns, correct? And then you're gonna get like 32 million volts. Okay, so it feels like you're getting energy for free, right? But in physics, this cannot be possible because like conservation of energy is sort of like the grand law of the universe, right? So it turns out voltage is not the only thing, right, that affects power, or in this case energy, right? Power depends on not just voltage but crucially also on current. Okay, and that's where your energy can be balanced. So in an ideal transformer, the primary power is equivalent to the secondary power. Okay, because of that, so IPVP equals to ISVS. Now, what I advise students, right, is don't memorize this formula or the other relationship ratio formulas that your school gives you, but rather remember this. Why do I say that? See, if you remember this formula, right, suppose you have a non-ideal transformer. Right, you have a non-ideal transformer, and then maybe the question tells you, right, that okay, for this particular non-ideal transformer, it is 90% efficient. So if it's 90% efficient, then I can actually just adjust this formula accordingly. So since it's 90% efficient, that means 90% of the primary power goes to the secondary power. Right, I'll just take my formula and then adjust it, this way. And then I see what the question gives me. Maybe they ask me to, they give me some light bulb, so there's some resistance. It could be in series, it could be in parallel. I just calculate what's the total power dissipated, in the secondary side, right? And then from there, I can back calculate the current or the voltage in the primary coil side. All right, so it really depends on what kind of question it gives you, but you see, I now have the flexibility to, adjust for non-ideal transformer. Okay, there are a few sources lah of uh, energy loss and efficiency, right? So your school notes may have a lot, but what I personally find, right, is that you just need to remember two. The first one is eddy currents. Okay, so eddy currents, basically, what it is like is, something like this. See, in EMI, we also learn Lenz's law. So every time there is a change in flux, right, and current can flow, current will try to flow to produce a flux in the opposite direction, right, to cancel out the change in flux. And we have this one whole piece of iron over here, the iron core, which allows the current to be induced, right? So if let's say you have got, say, magnetic flux, so your field lines, and your field lines are going in this direction, right? And so there is a decrease in flux, let's say. Okay, so to oppose the decrease in flux, then the eddy currents will try to produce a flux in the same direction. Okay, so if you've got the opposite direction, take note, because you're trying to oppose a decrease. So the current, the eddy currents, will produce a flux in the same direction. So if you apply your right hand grip rule, right, so then in this case you will have a clockwise current to induce magnetic flux in this direction. Right, now see, so once current flows, then heat will be produced. So a lot of energy gets lost. So there's energy loss in the form of heat. Okay, this is actually wasted energy. We typically don't need your transformer to get hot. So one way, or one easy way to go about this is to use something called laminated core. Right, so you can think of this like the Indonesian kueh lapis lah. This layered, multi-layered cake. Right, so I take this metal piece, I slice it up into pieces, right, and then you add this laminate in between. Okay, so this is a non-conducting material, right? So it kind of blocks your, eddy currents, right? From all these massive eddy currents from flowing, right? Thereby weakening or making the eddy currents much smaller. So you get a much smaller heat loss. Okay. The next one is flux leakage. So if you recall earlier, I was saying that, when there is a ideal transformer, we are assuming that the amount of field lines on the primary side is the same as that on the right hand side. Now, once there is a flux leakage, right, so there's a field line on the left hand side, but it doesn't make it to the right hand side. Something like this. You see, so there's a larger flux on the primary coil and a lower flux on the secondary coil. Okay. The easy way also, right? So all these inefficiencies are actually quite easy to work around. So is to coil them on a central limb. You see, so this is kind of it's like the ones that you all use at home for your charging of your handphone. Not suggesting that you break it apart, but if you have a spoiled one, no harm is just dismantle one and then you look inside. Okay, because home the power socket, right, that delivers energy to Singapore homes, I think is about 100 or is it 200, 240 volts, I think. Right, but then the one that is coming out from your phone charger is only 5 volts because your phone can only take 5. So it's what we call a step down transformer. Right, so you have got a primary coil, and then see just next to it, you got the secondary coil. So by keeping the coils wound onto the same central limb, there is a limb underneath. Right, so by keeping it wound onto the same central limb, then we will dramatically reduce the flux leakage. Okay, yeah, so it's also mentioned below.